Hey guys, welcome back to another episode of Simuleos. Today is going to be an absolutely fantastic day. Let me go ahead and mess with my mic just a little bit. Okay, I think everything's set. Let's go ahead and go over here. Now, today we're going to work on something a little bit different. Here's the thing. Some of you guys, if there is in fact anyone watching right now, may know that I missed quite a few days last week. I'm terribly sorry about that. Ended up being, I think, on Monday or Tuesday, I did a stream, and, well, it just didn't go right, you know? We were trying to finish up the vidder algorithm, we had a whole bunch of issues, and I don't know. I ran out of time, is basically what happened. I was doing some math the other day. I do a lot of math, but this was actually unrelated to any type of physics or anything like that. Basically, I realized that work is from, like, I don't know, 8 to, to be fair, I get into work around 9 and I leave around 6, but I also do work at home, where I'm reading papers or anything that I can do at home, I do at home. Actually, a lot of things I do at work I could do at home too, I guess, but, point is, usually after dinner I stay home and do the work. It's, let's say, 60 hours a week. Streaming is minimum of 20 hours a week. Then we have, YouTube, which is a minimum of 10 hours a week. It all ends up being that, well, added together, I'm working like, I don't know, 90 hours, which, let's round it to 100 hours a week. And I only have 105 hours total in the week if I sleep 6 hours a night. So what I found out was that I am kind of overworking myself, I think. Anyway, the point is, I apologize for missing the past couple streams. I don't know what I'm going to do about that. On the one hand, I'm thinking I might switch to just a Monday, Wednesday, Friday streaming schedule. On the other hand, it's not that big of a deal, I think I can still manage, because getting up in the morning and streaming, does kind of energize me for the rest of the day. So I think, I don't know, I'm still kind of 50-50 on that. And so I guess what ended up happening was I just kind of got burnt out a little bit, especially of doing the vidder algorithm. So I decided, hey, let's switch algorithms and let's work on something else. At the start of streaming, let's see, last year or so, gosh, it's been a year, we did a very simple, hey Gus Torn, geometrical optics type of thing, right? Where we tested to see if we could, do the invisible lens, which we're going to bring back up today. But here, what I wanted to work on is revisualizing that, because I figure, it's been sitting around for a while. It's probably about time to make a YouTube video on it. So, since we have Cairo, and we're able to draw kind of neat animations now, I kind of want to just draw an animation of the ray optics just kind of moving forward, going through the lens, and being manipulated by the refractive index on the inside of the lens. Now, there's a whole bunch of things that we could do with this, but I guess first let's describe what it is that we're talking about. So let's go here, let's open up Zernal, and let's get started. So, what do we have here? Let's go ahead. Yeah, I think it'll make a neat little video. Hey Lucky Box, actually, I've been thinking about this a little bit, actually a lot of it. The stuff I'm interested in is like stuff that I haven't seen before. So that's going to be like weird quantum algorithms and algorithms dealing with, I don't know, like, hey I care, algorithms dealing with, I don't know, like, weird finite element things or hydrocodes or something like that. Something that is significantly or decently advanced, but also gives you an intuitive feel for what the system is, right? But I've been thinking about it more and more, and I was speaking to a friend about it, and we're both kind of in agreement here. That kind of stuff is not the kind of stuff that people will naturally want to watch, It's not like I'll be doing some sort of crazy finite element method with high dynamic meshing. Let's say I'm doing something like that in the future. It's not like people are just naturally going to want to watch that. I've got, not yet, but pretty close to, in the next few years, a PhD in physics, right? So in the next 3 years, I will have a PhD in physics. I'm on the track to get a PhD in physics, right? I don't think what I find interesting can necessarily be, how do I put this? Induced? I don't know. Like, I don't think what I'm interested in is necessarily what other people are going to be interested in. So, I was thinking maybe I should tone back the next couple of simulations so that it's intuitively simple. I get it. You guys get it. Everyone kind of gets it. And then we move back onto the more complicated things from there. We hop between things that are kind of complicated and things that are a little bit easier to understand. And by hopping between them, hopefully we'll get a community that is willing to kind of stretch the boundaries of what they currently understand, but is not necessarily full of, like, well, physics PhDs, you know what I mean? So, like, we get people who are interested in learning to learn things that they wouldn't ordinarily learn, if that makes sense. So anyway, I think the point is, I've been hitting things too hard, and it's actually been really hard on me, because I have to spend a lot of time preparing for every single stream, right? If I do something easy that I kind of intuitively get, it might be a little bit easier. I don't know. We'll see how it goes. Anyway, yeah, sorry, Crams. I've been a little bit late for a lot of these. Okay, so what are we doing? Well, let's talk about geometrical optics. We've done this before a long time ago. If you've been watching forever, you would have remembered this. This is probably one of my first, well, big series on the channel. The idea is pretty simple. We send light in, right? Something like this. It has some sort of angle here. We'll call theta 1. And then it comes back out over here with a different angle, usually bending towards the normal. Theta 2. Okay, the idea is that this is a refractive index of n equals 1, or air. And this is maybe n equals 1, 1.4. So not air. Could be glass or something. I don't know. Anyway, so the idea is that we can find the new angle with something very simple known as Snell's law, which is n1 sine theta 1 equals n2 sine theta 2. Okay, a super long time ago, we spent time working on this particular system, right? Again, some guys might remember it, some guys might not. It doesn't matter if you do or do not. The point is, we have some code that already generates a whole bunch of rays, sends it through a medium with a different refractive index. And then after sending it through this medium with a different refractive index, we watch the rays as they move around. Make it a diamond, it'll attract viewers. We could make a diamond. Actually, yeah, we could make a diamond. I'm trying to think. We're not doing prisms or anything like that, but we could do a prism if we're doing the finite difference time domain stuff again, which was a huge mess, but kind of fun. Anyway, the point is, we're doing basic geometrical optics. So the only other thing I have to point out here is that if we draw a single line here, we put a lens in the middle here, something like this, okay? And we draw some dude here, okay? He might be a little bit tall. That's okay. And we give the lens some sort of focal point here and here. We can actually create what are called ray diagrams. The idea is that we send one line through the origin, something like this, another line through the focal point nearest to us, and it goes out parallel over here. Oh wow, that's actually quite interesting. I didn't think it would do that. And another one over here that then goes through this focal point here. Pretend I can draw lines appropriately. So the focal point is something like this, okay? Then we get a new image on the other side of the guy. Except he's upside down. And here the idea is that we have basically taken our original image here, and we've created a new image here, which is the image you see through the lens. And this is known as a ray diagram. In some sense, this is what we're visualizing. A whole bunch of rays being sent through a new refractive index. However, the refractive index here, what we're doing is we're varying the refractive index. So it's no longer a static 1.5 or 1.25 or something like that. Now it varies with some sort of crazy formula. Now, I don't remember all of the things we did. So what I'm going to do is I'm going to kind of take some time to remember what we were doing back in the day, and then we're going to go back and kind of manipulate the code, create some visualization scripts for it, you know, just kind of mess around. It's a weekend. I'm still kind of working on what we're going to do next. I'm sorry, I don't know if you could hear that or not, but I'm thinking about doing some kind of fun simulations with just billiard balls. I know it sounds kind of silly, but I actually had some really cool ideas for, I'll just go ahead and draw them out. Why not? New page before. And you guys can let me know if this is interesting or not. I think it's super cool, but I know. Yeah, you totally did. I think I'm going to, I can take a look at that in a bit. Okay, so here's what we got. Here's what I was thinking for another simulation for fun. Okay, in billiards, we have obviously 8 holes. Something like this. There we are. We have a whole bunch of balls. Let's see, they look something like this. 2, 3, 4, 5, 6, 7, 8, 9, 10, I think. Where this is the 8 ball. Okay, we have the cue ball over here. Pretend I can actually like draw. There's actually a way to hit this cue ball. Something like down here, over here, bouncing and hitting somewhere over here. Such that, thanks Addison. Refractive billiards? Well, kind of. Well, not refractive. Well, actually, I wonder if there's a way. There's probably a way to play laser. Maybe there's a way to play laser billiards with some sort of crazy laser beam, but what I was thinking was this. Just for another simulation, just for fun, I was actually just going to do a quick molecular dynamic simulation like we were doing before, except with billiard balls. And there's a way to shoot this ball such that only the 8 ball gets into a pocket. No other ball but the 8 ball gets into a pocket. Hey Husky. And I really wanted to see if it was possible to do this. Because I swear it's possible, but I don't know. The laser billiard game actually wouldn't be so difficult, I don't think. Once we get the geometrical optics stuff up and running again, I think that's pretty good. Yeah, we could build a game. I've never built a game before. Fine, we'll see if we can come up with some rules. Okay, how about this? We can work on some rules for some laser billiard games. We'll see. We'll see about the rules there. So I would imagine we have some sort of laser. We have a whole bunch of glass balls. If you shoot too hard, the ball catches fire. I don't think that's how it'll work. I mean, you'd have to. Okay, so we would have a whole bunch of balls. I don't know what we're thinking of. Now I'm totally confused here. So I could imagine how much processing do you have to do to determine the optimal angle and spin. I don't think we have to do spin in this one. I think spin is fine. Even so, spin I don't think would be that big of a deal. It's just a different way to hit objects. Yeah, balls are really fun to work with because they're like super easy systems. Physicists, for example, my logo is a spherical cow for a reason. I mean, physicists love dealing with any spherical object in a vacuum, something like that. Spinning lasers? Oh, come on, man. Don't make it too hard. Okay, we'll see what we can do. Okay, let's pop this over here. It's been a while since I did this geometrical optics stuff, so give me head counters like in pinball. Oh, actually, that would be kind of fun. Bumpers, yeah, I know what you're talking about. So we could like bounce the laser all over the place. There's already a game called Laser Chess. Let me see. Laser Chess. You can clearly see I was paying a lot of attention. This is okay, anyway, and sound effects, the more complicated you make this, the harder it is for me to code, but that's okay. What am I doing? Laser chess. Yeah, so there's this game called Laser Chess. Yeah, something like this. So one object shoots a laser, and your goal is to hit other objects. Open link. Let me see. Benedict bitterly me. Try it in your browser. What is this? I think I've seen this before. Yeah, I've definitely seen this before. This is actually almost exactly what we're doing, by the way. Except we're kind of able to move things around. Okay. Speaking of games, I started learning Mahjong a few days ago, and man, I like Mahjong. It's kind of one of those games that I would play on my computer all the time. A good bit of fun. But I feel like, I don't know, I'm tentative to make a game. Because going back to the discussion we said before, fine. It's fine to make a game. The problem is, the more you work on a game, the more people want more features, and I don't want it to be a situation where, like, I don't know, all of a sudden I spend like a month working on a video game, you know? Like, I'm fine spending a few days on it here and there, but, I don't know, I'm just tentative or afraid of things getting too crazy. I brought the concept from a game I did last semester. You play a ball of light and place spherical lenses to burn enemies. Wait a minute. Zadison, I borrowed the concept. Wait a minute, what concept are we talking about? Did you make this guy? The computer game uses the same stones, but not the real rules. Oh. I didn't know that. Well, I should probably learn the real rules then. Anyway, so let's go ahead and CD back a couple directories. Okay, so let's CD here. And CD projects, simulayos. And here's the question. Where I just typed in LSD into my terminal. LS. Okay. Japanese Mahjong. Open. Oh, I see. Okay, so I imagine, yeah, there are probably a few more rules than what I'm used to then. I'd say I'll take a look, but quite frankly, I probably won't have time. There's also a video game of strip Mahjong. One, named each tile 10,000. I bet you, yeah, there probably are a whole bunch of different rules. Use the same light simulation technique. Yeah, we've got a similar technique here. So let's see, what do we have? Maybe it's under FDTD? It's either under that or archive, not sure. LS Evanescent, CD Invisible Lens. That was LSD again. Do we have geometrical optics? Let's see, geometrical.cpp. Let's see what we got. VI geometrical. CPP. Looks like we have something. Static inline vector. Oh, yeah, this is not the easiest to read. Okay, let's see what we got. Normalized N. It looks like we have a code here. You know, yeah, fine. Let's put it somewhere. Okay, so here's what we're gonna do. Right, quit. CD, that was a VF. Man, I cannot type today. LS. Now let's go back another directory. LS. And let's go ahead and make a new directory. And we're gonna call this I guess we'll just call it geometrical optics. CD into geometrical optics. Now let's see. We want to CP, FDTD. We also have evanescent. Do you think it's an evanescent? Geometrical and evanescent. No, it's not. So let's do invisible lens. And now let's do geometrical as CPP and geometrical dot GP. So let's grab both of those guys. So geometrical star, put them here, and then let's also copy the make file. And let's put it here. Okay, let's open up the make file. See what we got. So what I want to do is change this to geometrical. So let's see what happens if we do make geometrical. 2 warnings, but it seems okay. It would be nice if you could manage a real-time simulation where you can drag the light source around. I would imagine if we were gonna make a game of this, we would have to we would have to do that. So let me do ls real quick. We have geometrical / geometrical. Okay, ls. What do we have? We apparently have geometrical.dat. Now let me see, geometrical.gp. What happens if we run GNU plot geometrical .gp minus? Oh, there we go. We have our invisible lens. Yeah. I was really worried this would take like half a day to get. Apparently it took 20 minutes to get. Okay. So what do we have here? Just for the record, in case people do not know what we're looking at, and let me just go ahead and export to image, just so we have this one saved. We'll say invisible lens .png. Save. Okay. So, the reason it is in, how do I put this? The reason it's in FDTD was because when I was originally doing the finite difference time domain simulation, I just decided we would kind of put everything there because that seemed like a good idea at the time. Okay, so what's happening here? We're running a simulation known as an invisible lens, and we've done this a long time ago, so let me go ahead and look up invisible lens. Lens with positive isotropic refractive index, something like that. This one. Give this a second, pop up. Here's the paper. Space mouse. Open link. 1 second. 3D connections. Kuriku shite o. Kuriku shite. Eh? Dagnabbit. Oh, that didn't help. That didn't help. Oh my gosh. Well, it's a new mouse. I got you that. I got that. Let me see. Huh. Okay. So anyway, the paper I just showed you guys was this one right here. Basically, the idea is that they created an invisible lens. By invisible lens, I basically mean that the light on either side of the lens looks exactly the same. You have all of these rays coming in, and they all come out on the other side exactly like what they had before. It's a 3D controller. 3D control. Oh, like for 3D simulations, like flight simulations or something. I still have it up. Let me see. Space Mouse Pro wa 3D connection no Japanese that I can't read. Puro. I'm sorry, guys. Why is it like mostly? Oh, maybe I can. Rest of Europe. United States. I love how they have a section for just the rest of Europe. Yeah, okay, that's cool. Yeah, I see that now. On-screen display. I wonder if it's... let me see. I've just been using my trackball. Anyway, back to the code. Okay, so the idea, right, is that we have a whole bunch of light rays going in. And then we have a whole bunch of light rays going out. But the light going in and going out is exactly the same. With the exception of a slight time delay, however long it takes for the light to bend around here. And the cool part is if we zoom in here and keep zooming in, it actually just like, how do I put this? You know, you can actually see the interior components of this. What do I press? A again? Yeah, A. So let's zoom in here real quick. And you can actually see the light bending around the center and everything like that. Now, what are we actually doing? We have a changing refractive index with respect to r. So we had some sort of circle. It's not a sphere, it's a circle. And at the center of the circle, we have some sort of refractive index, and it varies as it goes out, right? And so if I remember correctly, let's just play around with this code a little bit just so I remember some things. Let me ls. And let's go into the file over here, cd projects, simuleos, and I think it just made a directory geometrical optics, ls, and let's go into vi geometrical.cbp. If we go down to the bottom here, we have a whole bunch of refractive indices that we can play with. The refractive index that we worked with this time was this weird cubed root stuff. Now let me check github.com real quick. I don't remember any of it. So let me see. What I want to do is the following. So let's do this. GitHub.com. And let me see if I can find any of those formulas that, let me see, go here, your profile. Yeah, well, that's because no, I don't know. Let me see, I want to go to Simuleos, and let me see if we can find some branches, for contributors, pull requests. Here we are. Streaming file, proper matrix, sort. Okay. So let's see what we got. Proper matrix class. I know you sent it as a gist or something like that. No way we can find it now. Ah, dang it. I'm sorry, guys. I feel like I've let everyone down. But the idea is that we can change this index of refraction based on a whole bunch of different things. So let me see. I think it was an issue. We can look into issues. Let me see. Issues. Oh, there we go. Found it. That will be incredibly useful if I can remember how to plug it in. Okay. So difference is equal to distance. If difference is less than 0.01, index is equal to 1 over difference. And let's see, what do we have here? Okay. So let's just kind of move through this and see if we can remember a couple of different things. So what are we doing? Just for the record, how this code works, we have a couple of different guys here. So we have, let me see. In main, all we call is, we create an array of rays, and basically we say, yeah, so we give them all particular positions and directions and the velocities. The velocity being c. We give it a spherical lens at some sort of position with some sort of, let me see, spherical lens equals that. So we must have a lens up here. Online vector, inline, where's our struct? Inline vector operation, ray shape. Nope, that's not what I want. I want lens. Lens. N. Well, I know we have a lens, obviously. Now I'm just pressing N a lot. N. Come on. Simple lens. Oh, did I call it simple? I might have. Constant simple. A simple struct for a circular spherical lens. Oh, this must be it. Okay, so radius, x and y position. So here we give it a radius of 4 and an x and y position of 5 and 5. Okay, so then we have the ray, and we basically propagate it through. Where I believe, let me go up to the propagate function. Here it is, right here. Yes, so we have the rays that we're reading in, the lens we're reading in, the step size, which in this case is 0.01, so we have very high resolution, max velocity, and the output. Okay, and if I remember correctly, GNU plot was the part that took the longest about this, or longest for this. So what are we doing? We have refract. We should also have reflect, I think, unless I failed to add that in, which is something we need to add in eventually. Let's see, simple lens slab, inside of lens slab. Okay, so we have a whole bunch of functions just to check to see where we're at. But again, this is where the big stuff happens, right? So we basically just send a whole bunch of rays at this guy. We create some sort of cutoff in which the refractive index kind of changes a little bit. And then we're set from there. So let's see what happens. We have double R. I'm going to comment this guy out. And let's just do this. Just for a very simple test to make sure things are working. Double R is equal to distance, length, lens, origin. Okay. So we have R. And let's say the index is going to be equal to, let's just say it's going to be equal to 1 over R. 1 divided by R. Okay. Now let's go over here. Let's make... Yeah, well, okay, this is what I meant. The cutoff itself is kind of whatever we feel like. We could set it to be 0.1. Yeah, we could set it to be like 0.1 or 0.000000001. But yeah, it is related to the center, right? So the idea is that, yeah. Okay, so what I'm just going to do is 1 over R, and this should hit the same issue that Gustron's talking about. So let's go here and let's do geometrical. And now let's do GNU plot. Okay, so here we have an issue. The light goes into the sphere, and we run into a whole bunch of problems immediately. Okay, I remember we ran into these problems before. These guys are reflected off, which is good. That means that we have reflection working. Then we have additional guys happening in here. Now this is where things get kind of interesting. You'll actually see, as we get closer and closer, that this structure kind of repeats itself, right? And this is the utility in having a the cutoff, like we had before. Okay, so now let's do the same thing except with the cutoff. So we're gonna do the following. I'm gonna leave this commented out, and I'm gonna put in a quick comment saying that let's do it here. Come on. For what are we doing? Invisible lens. It's kind of yeah, well, it actually you weren't here when it originally happened, but when we originally saw these, it was so cool because I don't know, it was cool. Okay, so let me see. There should also be a way to make the GNU plot screen an appropriate size. Let me go to D and let me VI geometrical.gp. Okay, so there should definitely be a way to set the size. Here, let me do a couple of quick things just to make quality of life a little bit better here. So let me open up. I'm gonna guess it's in FDTD, and then I would guess it's in invisible lens. And let's look for all the GPs. Oh, I have a lot of stuff in this directory. Geometrical.gp. I'm looking for fdtd.gp. fdtd.gp. Okay, set palette defined. We were experiencing formulas like 2 streams straight. I know, right? I don't know. It was super fun, though. I remember just working with things and just playing around with things. Okay, set object size. 1 second. I'm trying to remember set terminal size. That's probably what I want. Set object size. Let's go here and do set terminal x11 size 1250 1000. Now let's run GNU plot. Good. So this one sets it up at the right size. I'm not sure exactly what's happening with these lines, but that's okay. It's a little bit easier to see, I think, if they're big like this. Now, let me see. There's probably one more thing I want to fix. Geometrical optics. Set size ratio object circle at. Is there a way? Palette color. Palette define object circle size. Line with 3. So what I want to do, object circle 44 empty border 3. Let me see if I do line width 3 here. And then what do we do? Geometrical plot, geometrical line width 3 here. Right, quit. Geometrical. That didn't help. Let me go here. Let me do GNU plot. Oh no, not what I wanted. Sorry about this, guys. Give me just a second. I am failing miserably at this. Let's set this to 2. Can I set it without X11? Probably not. Yeah, that's what I thought. Set x11 size. I don't know. It doesn't matter. It's kind of doing what I want it to do. The only thing I wanted to do was open up the screen at the size that I could actually, like, you know, see it immediately. Yeah, okay. This seems to be working okay. So let's do A again. Now let's go ahead and do the cutoff. So the idea here is that I just reset the way that we plot it with GNU plot so that this size of the screen is big enough that we can see it immediately. Okay, so now let's go ahead and add in our, 1 second, our cutoff, and let's keep working on it. Geometrical.cpp, and let's see what we got. So we have cutoff. So we're going to say if fabs of r, is that a function that we created? Fabs. No, I guess it's some sort of, I don't remember what fabs mean, but it has to be some sort of absolute value. Fabs of r greater than cutoff, which means we are within the larger portion of the circle that we're working with. We're going to say index equals 1 divided by r. Okay, and then we say else, and we say index. We're just going to set it to a constant here, equals to 1,000. Again, guys, I'm just kind of remembering what we were doing before. Yeah. Thanks, Kesterorn. Let's write this, go over here, and let's do make again. Make. Let me see. Then we want to do /geometrical and run the last GNU plot. Okay, so this one, let me just press the A button. Okay, so this one, we do see that the light kind of moves off the screen, which is great. I think, yeah, that's what I was afraid was going to happen. Okay, go ahead and do A again. Okay. So let's see if we can mess with this a little bit more. Let's change the cutoff to be 0.1 here. And let's set this to be, I don't know, 10 or something. Write this, go over here, Control D, and let's do make geometrical. Yeah, maybe they are. Let's go into VI GNU plot. Geometrical.gp. And let's just set the line width to 1. In fact, we could just leave the line width off. It's probably fine. And let's do make geometrical. Oh, I already did that. Then we need to run /geometrical and GNU plot. Okay, this one did something a little bit different. Let me see. So we zoom in. Okay, so this one, basically all the light, let's go A, all the light that went into the circle. I think the make file, yeah, we can make it do that. So let's do this, Control D, VI make file, and let's see, run simulation, /simulation here, and then we want to do, oh, is it make plot? Is that what we want? Let's go here. Right, quit. Make geometrical. Make plot. 1 second. 1 second. Make geometrical plot. Fine. VI make file. Let's go here. Bins. We want to do CSS flags. Plot. Let me see. If we do just make plot. 1 second. Let's do make file. CSS flags. 1 second. FTTD. FTTD. Let's just say we want to read in just geometrical in this case. So we want G++, std, all that's fine, simulation, here. So let's go and say the following. So we're going to say sim equals geometrical. I think we're allowed to do that. Make plot. There we go. Done. Okay. So now let's just kind of mess around with things. The first thing I want to do is see further to the right. I don't remember how to do that, but I'm apparently cutting everything off at some point. So, or maybe it's because no light goes that way. Let's do this. Let's change the refractive index to something rather standard. So no matter what the refractive index is, let's say 10. So let's do Control D. Then let's just make plot. Oh. Huh. That didn't go nearly as far as I was expecting. I was expecting to go way farther than that. Okay, let's change it again to 1. Write this over here. Control D, and let's make plot. Okay, that one did kind of what I expected, I guess. Let's allow these guys to go for a little bit longer, up to the top. Or let's lower the, we go down to main. Let's lower the, 1 second, dx, essentially. And let's go to Control D. Make plot. I might have forgotten to write. Control D, make plot. Nope, okay, 1 second. I don't remember how to do this. So max velocity output, propagate. Let's go through the propagate function and see what we got. It seems like they're being arbitrarily cut off at some point. Propagate here. Okay, so we have a whole bunch of rays. Move simulation every time step. So how many time steps do we have? Step size, constant length, double, max velocity. Then we have rays, output. Okay, so rays, size t I equals 0, time resolution. Yeah, let me go up to time resolution. Here, and let's see, here. Looks like... That's a lot of time. Let me do make plot. Nope. No, it seems to be right. Control D, make plot. It seems to not help here. Okay, let me go back down to propagate. Let's see what we got here. Let's see, propagate, vector speed, previous index, n of 2. I'm doing something silly here, and I don't remember what I did. If ray passed through refractive index change, n1 not equal to n2, that's fine. Vector n, normal at, vector speed, all that seems fine. Ray previous index, if output, ray p x, ray p y, ray vx, ray vy. So those are just the rays, position, and velocities. If I mod 1000 equals 0, so we're just plotting every 1000 steps. Seems fine to me. Size t, less than time resolution, I plus equals 1. Sure, why not? I don't know why I did that instead of I plus plus. Just because it's bugging me, I'm going to change that to I plus plus. Okay. It's the topmost if. If ray px. Oh. Ha. You're right. So let's just go ahead and get rid of this guy for now. And let's do this, and let's make plot. There we go, exactly what we want. It looks like a, what's those musical scores called? Good, thanks, Gustrun. Okay, so, we know we can now go past that length. So let me do this then. Let me dd here, and we're gonna say if, we'll use fabs, why not, it's fabulous. Here, lens origin x plus lens radius plus 1. Let's see, lens origin dot x, that's where the lens is starting, lens radius plus 1. Let's change this to like 3 times the lens radius. And this should, yeah, it cuts it off, but not as far. So this way we do have some cutoff, because I like the idea of having a cutoff, but a little bit farther out. Good. Okay. Yeah, or, yeah. We could have also done that. Okay. So ray P, ray V, step size. Okay. Now let's go down and let's mess around with some things. So let me think. 1 over R, that's not what I want. I want something, let's see. I remember we just pulled some of these guys. So let me see. Difference is equal to distance, length, origin, and P. I could start a bit further to the left. I think the way I do that in this code, I think I start all of the lines at 0. And then I could move the circle a little bit. Let me see. Where are we? We're at 5, 5 for X. This must be X, so let's change this to... One second. Let's change it to 10. Control D. Make plot. Yep. Did I forget to write it? No, I seem to have written it. One second. It is of radius 4, of X location 10, of Y location 5. Has to be, right? Oh, you know what I bet? I know what I did. Let me do this. Control D, VI, geometrical dot GP. I think I actually did change it in the simulation, but I didn't change it here. Let's do geometrical. Could do plot. Geometrical minus dot GP minus. Yeah, we gave it a little bit more room. We can give it more and more room as we go along. That's fine. So now let's check some things. What do I want to check? Here's what I want to check. I'm gonna go up and let's just modify this. So again, Gustron gave a couple. Let's just remember some stuff here. So let's see. Difference is 0.01. Else index equals 1,000. Okay. So it looks like we stuck with that index equals 1,000 thing. So let's go back to 0001 and set this to maybe 10,000. And then let's change the index to, what do we have here? Diff is greater than 0.01 if branch. Index 1.0 divided by difference. Okay. So difference Q cut off. Okay. Where's difference? Do I use difference? Yeah. Why do I have both? No idea. Okay. So we're going to try something real quick. EXP of R divided by EXP of R. What did you say? Divided by R. And let's see what we got. Write this, go over here, Control D, and then let's just run make plot. Oh, did I write it? Make plot. Okay, yeah, this was one that did some weird stuff. So what I want to do is let it run for a little bit longer so we can see where these lines go. And also, I'm going to remove that last line. So let me go over to the top. And let's see, number of lines, let's do 9 instead of 10. Let's make plot one more time, just so we have something more symmetric to look at. Oh, that didn't help. Why didn't that help? 1 second. I think you should turn off reflection. Let me see. So we have these in here. I don't think those are being reflected. I think they're being refracted out backwards. Oh, that's really hard to tell because we're at like the resolution limit here. Let me see. So is this a DX or a DT? Light gen, what do we want here? Let's see if we increase this guy by an order of magnitude. Go up here and increase this guy by an order of magnitude. right here, go over here, D, make plot. Of course, this is going to take an order of magnitude longer to run, but that's okay. Give it time, you know? Give it time. We have nothing but time. Okay, now let's zoom in. Zoom in again. Zoom in again. Okay. Go down to the bottom here. Let's change this index to 1,000. Let's change the cutoff. One less. Control D, make plot. 1 second. Give it some time to run. I forgot how long this took. Okay. Yeah, so I think here we can see it a little bit more obviously. I don't think it's reflecting. I think it's just refracting. So let's go A. Okay. So what I want to do then, let's increase the number of lights to 11 then. Let's go to the top. Number of lights to 11. Right, this, go over here, Control D, make plot. Give it a second to do its thing. Q is unused. I don't remember what we were using Q for. Again, it's been a while. I need to kind of do a couple different visualizations here. Okay, so what just happened? What I wanted to do... Wait. How many lines do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we do have the right number. Oh, you know what? I bet I did. I bet you I know what I did. Okay, so let's go where we started all of these lines. Where are we? Define, refract. We want an odd, even number of lines. No, we want an odd number of lines. That way it's symmetric. Okay, so let me go to where we create the rays. So we have propagate, we have raise, light gen. Here it is, light gen. 989, or 959. Hey, what's up? This simulation done with electrodynamics or quantum mechanics in mind. This simulation is just with geometrical optics. We're not doing anything fancy. It's just geometrical optics. Now, a while ago, we did have some finite difference time domain code, which was electrodynamics, but it was quantum optics, and that was kind of cool. But for the most part, this is just basic, what you'll see, you know, freshman year in a physics class. So it's not anything fancy. All we're doing is changing the refractive index of the lens and manipulating that. So 1 second, where are we? We are in light generation. We have size ti, eyeless, and raise.size. Yeah, it's super fun. It's super fun. Okay, so what we're going to say is vector 0, 0, raise.size, I++. We also had quantum information, yeah, which is another thing I got to resurrect from the grave at some point. Because that was a super cool simulation. I just need to make it visual. I can't figure it out. Like, that was all math. All of that was math. I need to figure out how to, like, sell it, you know? And once I figure that out, then we're definitely coming back to that. Okay, so what do we have? Previous index is equal to refractive index at. That's fine. Position is equal to vector. What? 0, 0, 3 plus I times dimension x divided by number of lights. Good, okay. Number of lights seems fine. So what we want then, let me think here, 3 plus I times dimension dot x divided by number of lights. That actually seems fine to me. So then we have 3. Why do I have a 3? I don't remember why I have a 3. I also don't remember what I'm doing here with this vec command. So it looks like, it's a vector. Gotcha. Whereas 0, 0 is going to be the x position, and the y position is going to be equal to 3. Good, okay. So now we want, 1 second, I times dimension x divided by number of lights. I don't remember what the 3 is doing. I think I might have just put it in there arbitrarily. Who knows? Okay, so now we do I times dimension x, number of lights. What I want to do, and I'm going to show it to you guys one more time here, when we make the plot, it's really kind of bugging me. 1 second, let it do its thing. It's going to take some time. Okay, it's bugging me that this bottom line here is not symmetric with any of the other lines. Pander's code, setup looking like the 90s. It is. 3 is probably so that it doesn't start level in start in level with the circle. What do you mean start in level with the circle? In fact, Panda Z Code, we are also using NuPlot right now, which is also the 90s plotting tool. So if you're interested, it's definitely interesting. Okay. Wait a minute, I'm thinking here. This has how many? We have 11, I believe. You know, I can very easily fix this. Super easily fix this. Yeah, I don't know either. That's okay though. We'll see what happens. So we have vector starting at 0, 0. Then we have I starting at 0. Let me go here. And let me run a simulation that's more easy to tell which one's in the center. So instead of doing R over R here, let's do 1 over R. 1 over R. Like this. Make plot. Ew. You think it might become symmetrical if we remove the 3? 1 second. Didn't we just do this 1 over R and it... Let me think. R is equal to distance. If we're greater than the cutoff... What did I do? It should be that if we have a line going through the center... Oh, I know what we did. We're running with 11 instead of 10. Now let's do make plot. There we go. Okay, so now we clearly have one going through the center. Okay, so let's see what we got here. We need to move in here and here again and here again. Good. Okay, so this center line then, let's zoom in over here. Let's see what we got. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th one is off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see what happens if we remove that 3. Yeah, I like these though. They're super cool. Okay, what are we doing then? A vector dimension. Let me see. Light generation. Man, these were fun though. Okay, what are we doing then? Light rays, velocity p. Let's see what happens if we remove the 3. I don't know what's going to happen. Could be anything. Who knows? Adventures with Simuleos. Oh. Yeah. If anyone's interested in sunlight, here's your sunlight simulation. That didn't help. Yep, let's add in the 3 again. Why was it a 3? Oh my gosh, I know I remembered this at some point. It has to be that we have some sort of offset, right? So it's going to be, without the 3, the Y position has to be... So we're starting at 3, plus I times dimension. What happens if we do 2? Let's change this to 2 real quick. Make plot. Sunlight, all is missing is an ocean. Ah, yeah, man, if only we had an ocean. Okay, so let's see what we got. Commands, gust run commands are available at... Good. Okay. Yes, so let's zoom in here. Let's see what we got. Okay, so it looks like... No! Not right. Well, I guess I could... It's not yet bright enough. I mean, it's still kind of dark outside. In like 30 minutes, it should be bright enough that I can move the camera around and I'll just keep it at the ocean for the rest of the stream. Why not? Who cares? Okay, yes, so let's go ahead and do A again. Okay, so 3 was the perfect number. 2 is a little bit lower. Does that make sense? Let me think. I should probably Control D, VI geometrical dot dat. Let's see what we got here. So it starts at let me see. 3, 2, 1. I don't know what I'm looking at. I have absolutely no idea. 7, 8, 9, 10. These are all negatives. Oh, here we are. Okay. So we start at 0 in x, exactly like we want. The next one starts at 2.4. Let me go to the top. This one starts at 2. Next one starts at 2.4. Next one starts at 2.8, has to be. Okay, so at 3, this means the first one starts at 3. The next one starts at 3.4. Does that mean we're counting down? This is me not remembering what I was doing, and unfortunately, I did not comment that one in. So let's make plot. Anyway, this one clearly has something going through the center, and it's going to be line 5. So let me go up to the top here. Very top. Drop this down an order of magnitude. And let's go down to our dx or dt, I don't remember what it is, our d something, and change this by an order of magnitude 2. Write this, go over here, Control D, make plot. Okay, this one goes a little bit less. Now let's do Control D, geometrical.dat, starts at 3. Next one starts at 3.4, 3.8, 4.2, 4.6, 5 must be the next one. Does that make sense? Okay, so the radius is 4. We're starting it at 5, 5. Good, yeah, that makes total sense. So because the orb starts at 5 in the XY plane. 1 second. Why do we go up though? It goes up to 10. Yeah, I think the last one starts at 10. And if the last one starts at 10, Panzer code. We are doing geometrical optics. So the idea is that we have a whole bunch of light rays going into a lens. We're modifying the refractive index of the lens such that the light does crazy things. And that's basically what we're doing at this point in time. We're plotting it with a with NuPlot, and that's all we're doing. In the end, it's basically geometrical optics following Snell's law. So what you'll learn in like freshman physics class. We did this a very long time ago, and we're kind of refreshing our memory on what we did. And eventually we want to run into, or better visualize this, and maybe turn it into something a little bit fancier. But at this point in time, we are just drawing a bunch of light rays going into a lens. That's literally all we're doing. So hopefully that's not boring to you, but that's what we're at. 1 second. Okay. So, and if you have further questions, I can answer those questions as we're going through. Okay. So we have C. Oh, this is all the refract function. Do we have? Yes, we do have reflect. Good. And we can turn off reflect if we want. That's fine. Okay. Quit here. So this means that if we start at 3, line 5 is going to be at 5. Which is what we want. Then we have, let's see, 1, 2, 3, 4, and then 5 to 9, which means the very last one. Let me see here. Dimension x divided by number of lights. Ray size. What happens if we just do ray size minus 1? Right here. Go over here and let's do make plot. That made it symmetric. That's all I want to see. So let's go down here. Let's change this to number of lights plus 1. Oop, that was not what I wanted to do. Plus 1. Up to the very top here, and let's change this to an odd number. So let's change it to 11. Write this, go over here to make plot. 152. Add in a semicolon. That was an L. Now make plot. That's not symmetric. Nope. It's not symmetric at all. 1 second. Okay, so we have that. Number of lights, 3. Okay, so this means we have to start this at 2. Control D, make plot. Well, it's symmetric. No, it's not. Dang it. I'm going to stick with 9 for now. Because I know where this one goes. So we go up here to 1, change this to 9, and then we should be set. Control D and make plot. Holy cow! What am I doing? 1 second. If we set it back to 10, Control D, make plot. What am I doing? Let me go back down here to light gen. Okay, and let me see what we have. So we went back to 10. Number of lights. Shouldn't add 1 to number of lights. Why not? Control D, make plot. Okay, that one's symmetric. No, it's not. Shoot. We are missing one. Or rather, we have an extra one. No, an extra 2 down here. Dagnabbit. 1 second. I thought we had it fixed, and I was an idiot and just didn't pay attention to what the plot was showing us. Alright, let's go back to not -1. Control D. I'm spending way too long on this, guys. Okay. It doesn't matter that it was never symmetric. I want to make it symmetric now. So here's the problem. I'm just adding an extra line down here. That's the problem. I want to get rid of that line. Let's try this. Make plot. Nope. Gosh darn it. I just wanted to get rid of that one line. I feel like I did this a lot. No, so the problem with that is if I make number of lights 11, then what's going to happen is Control D. We don't have anything going through the center. So if we make plot, in some sense, this is symmetric in that we have the appropriate number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have them all set, and I think they're all right. Like they're all symmetric around 5. But I wanted one going through the center. That was kind of, yeah, I wanted one going through the center. Ah, it's fine. Whatever. We'll keep it here for now. See, num lights is 10. Man, dang it. I thought we could figure this out, but I'm failing hard on that one. Okay, so let's go up here. And let's see. So we have a couple of different guys here. The reflections, if I remember correctly, make things a little bit weird, but at the same time, they're more physical, so I definitely would like to keep the refraction in. Let's see. So if I remember correctly, 1 over square root of r kind of looks the same as 1 over r, right? Let me go here. I'm kind of pulling from some of the Gustron stuff just to remember what we had before. Okay, yeah. So this is the one. All of them but this one are sent into the system. And it makes a little like, I don't know, it makes like a weird beak-like shape, right? I don't know if you guys remember this or not, but I definitely remember it. Basically what we have here is a refractive index that is changing from about this point right here as it goes outward, right? So now I'm thinking about this, and as we visualize this in the future, like as we basically show the lights moving through the system, this isn't the bird though, I think. This is just the head of the bird. Man, I like this though. I just remember how much fun this was. We got to mess with a whole bunch of different things, right? So there's a lot left to do with this simulation. What I want to do next is basically throw this through our Cairo stuff. I just want to draw a whole bunch of lines. I want to show the animation of the light moving through the system. And the reason I want to do this is because I don't know, I just think it looks good. And I'd like to get this ready for, how do I put this? I'd like to make this, a little bit cleaner, because new plot is nice. Don't get me wrong, it's super nice, but I think we can make it look better. I think we can make it look a lot better. Okay, so let's do A. Man, it's so weird though when you think about what's actually happening physically with this system, right? So first of all, how do I put this? The refractive index can't really be created in real life, right? I mean, you have to kind of think about that, right? Because we have to, you can make it with metamaterials or something like that. But here we have a system that we've created theoretically that is actually taking light and it is throwing it in all directions. And that's what's so cool about this simulation. That's why I was so excited about it last time, because like, come on, you've got this light that's just going everywhere, right? When you send in a standard set of rays, and it's absolutely fantastic. Seriously, by nicer, I mean, how do I put this? By nicer, I mean that it's more obvious what's happening. So I would like to start all of the light rays kind of going in here, and then have them progress through, like actually show the velocity as it's kind of changing through the system. So like show that the light's actually slower on the inside of the lens and stuff like that. So if we show the velocity as it's going through, I think that becomes way more obvious, at least in my opinion. Okay, so now one thing I want to do just to make sure, as a sanity check, I want to change this to just be a constant. So this is going to be 1.4. This is also going to be 1.4. Write this, go over here, Control D, make plot. That calls for Blender. Actually, in this case, I was just gonna, I mean, we're doing 2D plots, right? So I didn't think, I think we can just use Cairo for this one. However, Crams, you didn't tell me before. I'm working on it, Gustorn. Okay, good. Okay, just making sure this still works. Basically, we have exactly what you would expect. We have light coming into the system. It comes out, it refracts, and creates our focusing effect that we want to see before. I don't remember which ones of these were super cool and which ones weren't. Let me try the square root of this. So let me do square root of length of r. Is this gonna work? Oh, sorry, Crowns. Let me do square root of length of r. Wait, is it? Oh no, I think this is 1,000. Oh, d. I don't know what I'm doing anymore. My life is a lie. Okay, let me go here. Let me do 1,000. Let's go over here. Let's make plot. Yeah, that's what I thought. So, length of p, distance p. Make plot. Oh, wow, what? What's happening? I don't remember. Holy crap. What? Oh, this is actually super cool. Okay, wait. What is happening? Holy cow. What is happening? Oh, here, I'll show you what I meant, Krems. Just a second. What on earth? How did I forget about this one? We have two different axes of light coming together. What's that called? Focus. Focusing length. What? See, it's focusing here. No, it's not. It's not focusing, is it? Only these guys are focusing. Oh, well, that didn't help. What? These guys are focusing. Those three are definitely focusing. What? But why is it going off in straight lines like that? What on earth? I'm sorry. Okay. Krems, let me very quickly show you what you didn't tell me and is absolutely awesome about Blender. So let me do lscd back into the FDTD code, and then let's go into Evanescent. Now let me do, I think if I just run Blender from here, I can probably show you what I mean. So let's go here. Let's put it at the appropriate size. And let's change this box. So we should still have some sample data from before. So let's go here, change it to volume. Here, I don't know. Let's see if I remember how to do this. Voxel data. 8-bit raw. Oh, sorry about that, guys. Grabbing. What do I want? I want Simuleos. Where's that going to be? Oh, projects. Simuleos. Here we are. Then I want FDTD, Evanescent. Should be a .raw somewhere like that. Oh, do I not have a .raw file? Let's go back then. Invisible lens. Oh, I thought I had a .raw file. One second. Let's cd. Am I in the appropriate directory? I am. So let me ls star.raw. Nothing. So then let's just go ahead and run this real quick. So let me go into vi 3d evanescent.cpp. Go down to the bottom here. Seems fine to me. Okay, now let's see. We should have an evanescent dot. Oh, I know where it is. I'm sorry about this, guys. I was in the wrong directory. Visualization. Evanescent. My bad, guys. ls here. ls here. And here's what I want. So let me do mplayer. Actually, guys, can you see this if I run this? mpv tfsf 1.mp4. Can you guys see this simulation? Let me know if you can or cannot. This is one of the previous Evanescent field simulations we were running. Just basically a single wave moving through quantum optics stuff. Yeah, I did a very good job of describing that, didn't I? Okay, so let me do... Oh, good. So before I was having to run some weird mplayer thing, but I think MPV actually works a little bit better. Good. Okay, so let me see. What I want to do is the following. So let me run Blender. Let me resize the window one more time. And I'm sure there's a way to make Blender start at the appropriate size, but I'll worry about that later. So let's go here. Now let's do it. So I want to take this box, change it to volume. Go over here. Go to type. Let me see, voxel data. And then I want to change this to 8-bit raw. Go here, change it to the appropriate file, which should be projects, Simuleos, visualization, evanescent, raw plot.raw, sample.raw, sample save.raw, raw plot.raw, maybe. Change it to 128. 128. 128. We see something. We don't see anything. Nope. Let's try another one. 3D sample.raw. Okay, this is something. I just want to see something. Let me see if I can get this on our system. So let's see. I think I have to do this and go up here. And if I change it to this and maybe lower the density. No, that wasn't quite right, was it? What do I need to do again? I think density needs to be 1.0. Not modeling, just visualization. I distracted for a bit. Now we're doing 3D modeling. Yeah, we're just doing visualization of stuff. One second. Sorry about that. Let me change this to constant. And let's see. Density scale, I think needs to be 5.0, 0.5. I'm trying to remember how to get this to work. Let me do... Gosh darn it. I don't remember what I did. I'm just going to click all these buttons and hope something works. Doesn't seem like it did. If I lower the density? Nope. Okay. I don't remember how to do this, but that's okay. I'll remember at some point. But anyway, the thing that I thought was actually super cool that you didn't mention before, but is absolutely essential, or like really, really cool. If we move this to rendered mode, oh look, it's actually there. Okay. It actually will automatically render exactly what I want to see. This is so cool. I didn't know it could do this, but now I can totally use this for my research, which is fantastic. I didn't know, so I'm doing 3D stuff a lot like this. And I didn't know that we could switch to this view. And now that I know we can switch to this view, it makes it so cool. That is, I'm sorry, I kind of geeked out a little bit when I saw that that Blender could do this, because for the most part, the other 3D visualization software I was working with, you could do whatever you wanted. So you could do like, let's see, I guess solid or something like that. You could look around like this, but then you have to re-render every time. You can go, Crams. That was it. I just thought it was so cool when I saw it could do this. It's nothing special. I just thought it was really cool. So basically, you're right. Blender has a whole bunch of really cool uses, and I will definitely be using it more in the future when doing 3D stuff like this. Super excited to be using this for my research and stuff. Man, anyway, okay, back to the... sorry about being so scattered today, guys, but back to the 2D stuff. Okay, so let's CD into the appropriate directory, which should be, I believe, geometrical optics, ls. Yes, okay. Now let me run make plot one more time. Gosh darn it. So here's the thing. This is why I was so excited about this simulation the last time we did it. You can add a camera and animate it to fly around. Yeah, I know. I knew I could do that. But the fact that I could actually viewport render was something I didn't know, and that's really cool. Okay. So this is cool. Let me try something. Here's what I want to do. I'm going to send in light that is shifted a little bit. So let me go up here. You should spend some time to read about light fields. It may be useful for you. It probably will be. I'll definitely look into it. So what do we have here? Here. So I'm going to remove the 3 and change it to a 1. Write this, go over here, Control D, make plot. Okay. So what I just did is I sent light through the system, but only going through the bottom half. I know, right? I'm sorry. I forgot how cool these were. Okay, so here's what's happening. I don't know why it's moving along this line. I have no idea. Holy crap, what's happening? Let's increase the number of lines to 20. What the heck? Change this to 20. Make plot. I'm sorry, Zadison. I can't help you with that one. What the heck? I don't know what Marmot Day is. So it's no longer random? What do you mean random? Panda Z code? I don't know exactly what was random before. Sometimes I mix up the words random and arbitrary, and I apologize for that. When everything is the same as the day before, maybe. I'm sorry. I apologize. I just kind of completely forgot the simulation was here, and now that I remember, it's kind of like, I don't know. It's super cool. You said the rays were scattering randomly. No, yeah, so they're scattering in a predictable way. I just don't understand the predictable way. Let me change this again. So let me go to, let me see. Oh, Groundhog Day. Yeah, sure, that's something. But that's a movie, I think. Let's go here, change this back to a 3 in the light generation. Yeah, let's change it back to a 3. Actually, no, let's keep that a 1. I'm wondering, with that last simulation we just showed, let's go to 20. Go here, make plot. Okay, there's one thing that is kind of bugging me about this. Okay. So we have this kind of like racetrack thing that's happening, right? And they're all approaching at a different angle, but slightly different angle, right? Okay, so that makes sense then. Because they're all approaching at a slightly different angle, they're all shot out at a slightly different angle, which means when they hit this part, which that's the edge of the circle, they all come out. Okay. Yeah, I can get behind that. Now, what's this guy doing? There's one aberrant ray. What's it doing? It has to be the one that's going through. Yeah, so it's the one that's going through the center. Okay. So now, let's go down here. The reason I put it through the bottom is because I wasn't sure, and I'll show you why in just a second. Propagate. No, I want light gen. Change it back to 3. Go here, Control D, make plot. Yeah, so right here, the problem was I wasn't sure which ray was going where. I suppose it's obvious now, looking at it, that one goes down and the other goes up. But I don't know, for some reason at the time I wasn't quite clear. Okay, so let me see. What I want to do then is change the cutoff. So let's change the cutoff to be super small. Ridiculously small. So let's do, so it's never going to hit this cutoff. Control D, make plot. That didn't fix the problem. Did I write it? Oops. 1 second. Control D, make plot. No, it didn't fix the problem, which is absolutely insane when you think about it. So what's happening with these guys up here? The very first ray. Oh my gosh. What? Okay, wait. So what are we doing? So length of P. Length of P. So P, where's the length? Oh, 1 second. Length. Oh, that wasn't what I wanted. Alt tab. Length. Here. Length of ray vector. That's fine. Make the index at the cutoff the limit of the function. I don't think it's going through the cutoff anymore. I think that's just how it's supposed to be. So let me see, where is our length function? I'm pretty sure yeah, length of vector A is the square root of the dot of A times A. Okay, so A, the dot product, simply the dot product, right? So let me see, if we are reading in P, what's P? P is going to be inside of lens P. So where do we read P in? Vector P. So refractive index at, it is going through the cutoff. Well, let's just remove this else statement though. Or we could do this because it doesn't really matter that much. Here. Control D, make plot. Yeah, so even when we do that, it's still doing that weird thing where that one first ray is for some reason a completely different angle than the other rays. But that's okay, that's fine. If that's how it is, that's how it is, you know? Not gonna... by far the most interesting programming stream. Oh, thanks, Pander's Code. Dude, you're putting in 100 frames per second GIF? Let me see that. Like, put it in the chat. And I will totally take a look at it. Okay. Oh my gosh. Man. It's not that big of a deal. If that's how it is, if that is the end result, that's the end result. I mean, that's it. It's weird. So let me see, what are we actually putting in though for this, at every single point in space, what is the refractive index? That's the question. So we have the index here, square root of length P. I'm trying to upload 60 FPS, but has a frame time resolution of 10 milliseconds? Frame time resolution of 10 milliseconds. Yeah, I'm not sure. Every time I put up GIFs, it's always of like my simulation or something like that. No one ever looks at them anyway, so. Okay, so what do we do then? Square root of length P. And what are we doing then? Okay, P. P is going to be a vector that we're reading in. Let me see. We're putting it in refractive index at. So let me go to the refractive index at. Refractive index at. Here. Okay, so we're reading in ray of P, and what is ray dot P? Ray dot position. Okay, so we're reading in its position. Okay? So if we're reading in its position, then its position is going to be X and Y, And then we're returning the dot product of x and y. So we're returning x squared plus y squared. Okay, working on that. X squared plus y squared. So if we're returning x squared plus y squared, that means that we're returning essentially r squared at any given point in time. That's actually kind of cool. I don't know why they go off linearly like that. Does that not boggle anyone's... Fine. Whatever. It's only me. Okay. Let me move on to another one then. We have all these different guys. We might as well... I've spent the entire day just kind of refreshing my memory on this. Oh my gosh. Okay, so let me just kind of... We have a couple of other formulas here we can kind of go through. I remember we went through a couple of them. I don't remember what the error function did. I think the error function actually gave us an error last time because we didn't have a reflection in. Let me see what happens if we put it in this time. So what we want to do... Of course you'd say to do them all. You gave me all of them. Ah, man, that was so... You know, guys, 1 second. I need to pull out my lab notebook, and we have 30 minutes left. Yeah, we can do them all again. I mean, it's been months since we did this before, right? I'll show you in just a second. Let me write down the particularly cool ones that we hit, just so I have them as a reference for the video later. I don't remember. I will take a look in a second. Notes on VBots. Okay. So let me just write down very quickly. Geometrical optics. Geometrical optics. Let me see if I can find a place to put this notebook. Of course, my desk is completely littered with things it shouldn't be littered with. Anybody ever have that problem? No? Okay, it's just me. That's fine. I'm a mess. In general, my life is a mess right now. I don't know what I'm doing. PhD, I don't know. Okay, so, let's see. I'm going to write down the square root of the length of p, because that one is particularly interesting. So, let me see. And also 1 over r. Square root of the length of p. Okay, let me try another one. So what we want to do then, the error function, Gustron's saying it didn't give us an error, but I'm pretty sure it did. We'll see. So we want ERF. 1 second, Zadiston. I will take a look in just a second. ERF of 1.0 divided by difference. So 1.0 divided by r. Go down here and let's set this to 1,000, just so we don't run into any issues. And change this back to 0.001. Okay, write this. Go over here, Control D, make plot. What? Oh, did I forget to write it? Control D, make plot. Yeah, okay. Okay, so, let's simulation the made into my game. Let me see. Oh, dude, super cool. That looks really... Like, okay, so I guess you've got 3 lenses here, right? Is there any way we can make it bigger? I guess that works. We could totally use this for some sort of light bowling. Let me think. How do we do that? Alright, we gotta come up with rules for light bowling now. I don't know how, but you totally need to come up with rules for light bowling. That sounds like a lot of fun. Okay, so what's happening here? Gustron was right. It didn't give us an error. Let's see what happens if we zoom in. Oh, no, that's interesting. Let me zoom in just to the ball. Didn't we talk about light bowling a second ago? Wow. Wait a minute, what's happening? Okay, so we have light going in. What on earth? Okay. Every time. This happened last time too. I kept plotting these and I was like, wow. Okay, Oh, I'm sorry. I'm sorry. I meant billiards. I didn't mean bowling. I did not mean bowling. My bad. I meant billiards. Man, the error function. Am I just going to write all of these down? Because I think I'm going to write all of them down. Error function of 1 divided by r. Let me think. So, what happens if we just do the error function of r? I don't remember what that one looks like. But see, here, this is the cool part, right? You have all this light going into the system. Some of it's reflected out. That's fine. The stuff that's reflected out makes sense. It should be reflected out because that stuff is like, well, it's being reflected out because it's supposed to be reflected out, right? However, the stuff that's going into the system is coming out in this incredibly bizarre way, right? You've got, I don't know. I don't know how to describe it. It's like, I don't know. It's just physics. Not real physics. It's theoretical physics. Okay, so let me do this. Write this. Go over here. Control D, and let's make plot. What? Maybe you did, but okay, wait. The light's going into the system, and then it's just saying, I don't want to be where I was a second ago. I'm just going everywhere else, just wherever else. I'm just going. No, I don't think. It's like we put a rock in the way. Like there's a stone right here, and like the light's just going everywhere. That was the error function of just r. By the way, what you saw was 50k rays evenly emanated from the light source, resulting in 3 to 5 times as many lines being rendered. Yes, so that's something we can do, but I'm not looking at it right now. We're doing small numbers of rays right now. We need to figure out how to do that, though, I suppose, to make it look more visually appealing. Because your stuff looked great, it's Addison. It looks absolutely beautiful. I'd love to be able to visualize something like that in this system. And I think we can. I think we totally can. I just have to think about how we want to do it. Okay, so now let's see what else do we have? We have, I think one over cube root and one over square root were about the same, right? Let me do 1 divided by cube root of r. Let's D, make plot. Yeah, so cube root is just a little bit longer than square root, right? So and 1 over square root of r. We go over here. GPU acceleration was a bit of a pain, but didn't make it into the final product. Yeah, I understand. Panzer Code, will you be doing that today? I will be doing it probably tomorrow. I stream for 2 hours every morning. Well, man, I forgot how fun this was. Okay, so I will probably be streaming every morning from now on, from 5 to 7. I've been missing a few days here and there. Again, it was my own fault, no one else's fault. Okay, what else do we have? Error function, cube root, square root, error function, this guy. Sure, I'm just going to plug it in. Why not? So let's go here. Index equals this guy. And then we're going to change this to R. There, and change this to R. Zadiston, what are you trying to achieve right now? Right now, I'm just plotting things. 1 second. What? Oh. Okay, wait, guys. It broke. 1 second, let me, how did it break? Pretty much, sorry. Ah, man. I can't explain this one. The code broke. That's the only way I can explain it. Let me see. So let's change the cutoff. Oh, I just closed a terminal. That one. Okay. What is the refractive index of the singularity of a black hole? Yeah, I can't answer that question. What is the refractive index of the singularity of a black hole? I mean, let's see. It's a refractive index that... So here's the thing. If we have a 1 over... It was meant to look like this? Wait, so you're saying it was meant to... Let's change the cutoff. So let's change it to 0.01, and let's change this to 10. Control D, make plot. Give it a second. What? Oh. Oh. Oh, that's so cool. That is so cool. I know exactly what's happening. Yeah, okay, wait. Let me go to the top. Watch this, guys. So if I increase the time, let's double the time. Oh gosh, if this works, this is so cool. We are retarding light. Not... Maybe. Yeah! That's so cool. Okay. How do I put this? Okay. So I don't remember what this function's doing. But what I do know is that the light that's going into this system is being slowed down more and more and more and being constantly attracted to the center, to the point that our simulation will never finish. So here's what I'm going to do, just to drill this point home. Let me increase this by an order of magnitude to 10. Okay, and now let's run this. Control D, make plot. Give it a second to do its thing. Oh man, that's so cool. That is, that's so cool. Give it a second. Okay. Dang, I broke it. Man, I thought it was working, but I broke it. Okay, so let's see what happens if we zoom in here. Zoom in here. Oh, I hit the cutoff. And then it reflected out. Oh, gosh. Wait. Let me go back down. And let me change this. Let's not have a cutoff anymore. In fact, let's have the cutoff do what I want it to do. So let's have the cutoff do this. Okay, let's right here, go over here, Control D, make plot. One second. Okay, this should do what I want it to do. In other words, we should go into the center, but we should never hit the center. I think. Give it a second to run. Should never hit the center. Come on. I'm waiting. Will this run in time? I guess I'll take a look at this link while I am, waiting on this to work. Ray tracing. Oh, super cool. Yeah. Oh, it worked. Oh, totally cool. Okay, wait, let's pop this back over here. Okay, let's see what happens. We're gonna zoom in here. Okay, we're gonna zoom in further. Yeah, there you go. Look at how small this hole is though, guys. It's like, that's 0.9, this is 9.99. This is 10.01. This is 10. So this is like, this is 0.998. The entire radius of this, or the entire diameter of this circle where light just isn't working is, how do I put this? It's 0.004 in size. I don't know what I've made because Gustorn gave me the formula, but we can totally look into it. Man, that's cool. That is so cool. Gosh darn it. Okay. So if we just zoom in here though, right? It just, man.
That is absolutely brilliant. I love that. Okay, shoot, what am I doing with my life? Okay, so this is exp of 1 over cube root of the difference times 1 over difference. Okay. So what else have we not done? We haven't done this one or that one. So we'll just go ahead and do those two, and then we'll call it today. Call it for today, I think. So let's run this one. Oh my gosh. Let's check this guy out. Do the very last one. The Batman code. That one, if I remember correctly, that one gave me trouble last time. Let me do 1,000 or 100. 100 should be fine. Let's go over here. Control D, make plot. What? Oh, the Batman formula. If I remember correctly, that one was hard to. Okay, we'll see what happens. Give it a second. Index 1.0. This one didn't even go into the circle. 1 over difference. Oh, that's because we don't have a difference. So it's unknown. These need to be R's. Hey, Edge226, what is up? R. R plus 1. Make plot. Okay, now let's see what happens. There we go. Okay, this is what I expected. So let's zoom in. Okay, I don't know what's happening. So let's zoom in further. And I guess further. And... cool, Edge. Dagnabbit. Let's go here. Zoom in just a circle, I guess. Okay. We have light going in. And it is... I'm sorry, Gustorn. I expected something that I didn't understand. Name curves, for example. Yeah, I think we've totally done the Batman curve before on this channel. I'm just really bad at implementing things. Okay. The problem is I have no way to physically interpret this one. I don't. I don't know. Now, oh man, what would be super interesting? Popular curves. Randomly colored mu-like curve. They have a Jay Leno curve? Mew. Is this Pokemon Mew? We'll see. Okay. So we have one more function to look at. And then, okay, we can look at the Batman one too. Let's see, this one. Let's pop over here. Add this one over here. Actually, what happens if we don't have a cutoff on this one? Let me go back to the previous one. Oh, if we don't have a cutoff on that one, it's going to break. So let's go here. Oh yeah, definitely looks cool. That not... Okay, write this, go over here. D, make plot. That one, of course, broke because I did the same thing I did before. So let's go to diff. Let's change this to R. And the next diff. Change it to R. Next diff. R. Next diff. R. Yep, thanks, Panzer. Write this, go over here, Control D, make. I think that one is a gamma correction formula. You know what's weird about this one? It's like it's trying to... It's like it's trying to go to a focal point. It's like it's trying its best to go to a focal point. But from GitHub list, name curves, well, cow curve. Maybe I could use the cow curve in my formula, but it's like doing a very bad job. You see what I'm saying? Of coming together. It's like I don't know, like a group of, I don't know. It's weird. It kind of looks like, I'm gonna stay away from things that kind of look like other things. It is exactly what I thought. U-curve. That's pretty cool. Okay. So then I think the only one I haven't done that is on the list is the Batman curve. I believe that's what this one is. So I will copy this one and we'll see what happens. What do I do? Copy the whole thing. So let's just go ahead and do that. There we are. Over here, let's add in, I guess 8 spaces. That was 9. Yeah, that's okay. I guess it had to be 12 spaces. Yeah. Okay, let's make plot. Oh, that one does. Aw. Okay, let me see something. Just do double diff equals R. Oh, I just yeah, you're right. 1 second. Double R equals that. Double diff equals R. Make plot. Okay, there we go. We have something weird. Okay, let's zoom in here. Okay, I remember this one. Yeah, actually, I don't use any other diffs, do I? Okay. Okay, let me take a look at this a little bit closer. Okay. Okay, so the light. First of all light is going into the circle. That's good. All the light is going into the circle. Really cool. Okay, but I actually don't even know what that word means. Thonic? Subterranean? Translation meaning the deity spirits underworld? I think it was the Batman function. Wasn't it the Batman function, Gustorman? Okay, so let me take a look here. We have the light. All of it's going into the circle, which is great. In here, we have some of the light refracting out here, and some of the light just going right in, and then it just goes. It's like it doesn't know what it's doing anymore with its life. I mean, this perfectly describes the struggles of your modern PhD student. Not knowing where he's going with his life. Some turn away, some carry on through but don't know where they're going, and then there's that one guy in the center who happens to get a Nature publication and just he's set. I don't know. Okay, so we got to do a whole bunch of things, and the question of where we want to go with this is kind of sort of up to you guys. I'm gonna run some new basically visualization scripts and stuff like that. That's what I'm gonna be working on in the next few for the next few episodes. Reason I want to do the visualization scripts, selling us modern art. We could though, couldn't we? I want to run some visualization scripts of this just to show the light moving through the circle, doing things like that. And other are not even in the picture. You're right. What's bizarre is how far. I mean, look at how far this. That looks like an arrow pointing towards chaos. But how far this one guy goes. Right? So this one guy. I guess that's also kind of a metaphor. He goes way, way off in the wrong direction. I suppose all of these guys would go way, way off in the wrong direction, though. Let me go up to the top. Can't read that one now, can I, Zadison? Let me go up to the top and let me remove, we have a propagate function. Here we are. And let me remove this if statement. I bet you I'm just running the simulation for a little bit too long. In fact, I know I'm running the simulation for too long because I like quadrupled the, yeah, I ran the simulation for too long. So let's cut down on the time a little bit. Go over to the top. Let's drop this by an order of magnitude and a half. Control D, make plot. That's a little bit better. Okay, now let's go back down to where we did the propagate function. Here, next, there, next, there. Okay, and let's put these guys back in. Good. Okay, so we got a lot of stuff we can do. On the one hand, I would love to see a super cool looking, like Zadison stuff. The stuff that he showed us a second ago, that was so cool. Let me see, where is it? I know I couldn't have deleted it. Did I delete it? Zadison. Starless, no. I don't see any imager. Ray tracing, nope. I must have accidentally deleted it. Let me go, where is it? It's, page up. Here. Open link. Page down. Yeah, this stuff looks really cool. If we can make our simulation look something like this, that would be absolutely beautiful. Of course, we still have other things that we can do here. We mentioned light billiards, which is something we could do. Can we see that Pokemon function? Finish loading. The Pokemon function, let me see. Here it is right here. Do we have... Let me see. Yeah, let me see. What we need to do is figure out if it has... That's going to be really hard to do. So the problem is that we need some sort of well-defined function to work with. The top of the Batman curve kind of worked because, you know, it's okay. But this one's going to be hard because it's like it's like overly defined in X, Y, and Z and stuff like that. So I have to kind of think about how to do that one. We might be able to look into it in a bit. But I think that's going to be it for today, guys. We went back through, we kind of refreshed our memory on all that old geometrical optics stuff. I kind of regret closing that book so early. We should have let it kind of go a little bit further. But this will definitely make some really cool videos and stuff like that to put up. I'm really looking forward to it. So what I've got to do definitely, let me go here. I'd love to plug that refract into my rendering code, but it doesn't support varying refractive indices at the moment. Yeah, so that's kind of the thing. It actually took some playing around to get it to work. So for the record, that invisible lens code, let me see. Let's go ahead and just plug that one in just so it is there. DD here. DD there. Up here. I know a little bit about fluid dynamics. If you need to ask a question, feel free to, but I don't know if I can answer all the questions. I'll tell you if I don't know the answer to that or if I'm not confident in the answer to that. Okay. The invisible lens code does not seem to be as invisible as I thought it would be. That's weird. Maybe it's because the cutoff is different. Yeah. Okay, I see what's happening. Make plot. Yeah, that's what's happening. Okay, so what's happening, let me think. I was looking at it the other day and wanted to make a simulation out of it. Oop, that wasn't what I meant to do. What did I do? Open link. Gotta click on the button. Okay. Let me see. It looks like, oh, that's gonna be a pain to do from scratch. So what you've essentially got here is a vortex of a fluid inside of a fluid. What you're doing is you're rotating the system, and you could do this with a hydrocode or something like that if you wanted to. The problem is fluid dynamics is like incredibly, how do I put that? It's incredibly, how do I put it? It's fluid dynamics is hard to get into. And running a simulation that is this advanced is something that you might want to use some sort of stock software for, in my opinion. Now, that said, there is probably some software out there. There's probably a better way to do it on your own. Like you could probably write it on your own, but it's gonna be really hard to do on your own because of the way you have to like resolve the grid and stuff like that. You have a couple different simulation methods. You have a particle-based fluid dynamic simulation that you could probably run, and that would probably give you the best results. I don't remember the name of that one. It's what is it called? It's like a particle. Dang, I don't remember the name of it. But it models the fluid as if it's a bunch of smaller balls. And I think that would be your best bet here if you want to try it from scratch. If you don't want to try it from scratch and you want to use some stock software, there's probably some software that'll do it for you. Okay, let me plot this one more time. Make plot. Okay. And let me see something. Else are cutoff, cube root, index equals 1. Let's change the cutoff one more time. Make plot so that only the middle line goes through. Why is this different than what it was at the start of the stream? Yeah, I don't know how to do that, honestly. I've only done fluid simulations a few times. And I think, let me go up to the top. And I think it's not the easiest thing to do, but I'm not discouraging you from doing it. I'm saying I don't know. Okay, here's the invisible lens we started with. I think I know the problem. Let me see. SolidWorks, products, flow simulation, open link. Yeah, something like this will probably do. SolidWorks is very well known. However, I think you have to pay for SolidWorks. I think it's expensive. Okay, so this is the invisible lens we started with. However, if we increase the number of rays, for some reason it doesn't work anymore. So let's go over here, Control D, make plot, and let's see what's happening. So it looks to me like some of these rays, oh, I know why. Some of the rays are getting cut off as they're going through the center. No matter what, we're going to have some rays that are cut off through the center. Yeah, that's probably going to help you out if you want to do some sort of GPU computing method. But this is pretty close to what we want. And I'm pretty happy with that. So, overall, we checked a whole bunch of different, what are we going to call it? A whole bunch of different varying refractive indices and stuff like that. We have a lot left to do. Tomorrow I'm going to work on making this visualization a little bit easier to understand in terms of basically watching the rays as they move through the lens. And we have a whole bunch of things like that to work on. Today I'm probably going to go ahead and make a video on the traditional Huffman encoding. I realized I kind of dropped the ball on the dynamic Huffman encoding when we were like right there next to the end. Totally get that, but I gotta be honest, guys, I lost some motivation to work on that. So I'm not going to, I'm gonna pick it up later, but not now, in a bit. And by a bit, I mean a while. And by a while, I mean, I don't know when. It's still on my radar, but I kind of pushed it off because of X, Y, and Z. Not Pokemon X, Y, and Z, but just X, Y, and Z in general. Anyway, good. So we went pretty far. It was pretty fun to see this again. I agree, Gustorn. So let's continue working on it. We'll kind of get some videos out on it. I'm sure we can actually make a couple videos on this kind of stuff, but for now I think one video is good enough. We could also take a look at the FDTD stuff again because that light stuff was really cool to look at, but again, we'll kind of play it by ear from here on in. Anyway, guys, thanks so much for watching. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time, and I will see you around next time for the next episode of Simuleos, where we continue working on geometrical optics, finagling it to make it so we have these simulations kind of in some sort of GIF format or something like that, so we can kind of easily share them. And then we're going to worry about making it look cool. After we have this, what we just showed in Cairo, then we're going to try to make it look cool. And we'll see how far we get there. Anyway, guys, thanks again. Real flow for cool looking stuff. This must be another fluid simulation. Yeah, definitely. Good. Okay, guys, so I'll see you next time. Thanks again for watching, and have a great time doing whatever. Bye, guys. See you around.